Dear all, welcome back to the Huffman coding algorithm. So we'll be studying the Huffman coding algorithm in depth. This is one of the important greedy techniques. This follows greedy algorithm. So first we'll be observing the concept, and then we'll move towards the codes, and then we'll be composing the entire code. In today's video, the main thing that I will teach you how to write the code from the algorithm. So before we understand the concept and theory, let's have a look of the code. Okay, so as you can see the code section, that is the code of Huffman coding. So first I've constructed the node that I will be using, and I will show you through understanding the concept that what is node and how we construct it, the code. So this is the construction of node, and here we have build a node comparator. So this is one more thing that we'll be utilizing the comparator class inside priority queue in Huffman coding. And then we have started the building the Huffman coding. So for this is generate codes. So here we have generated the codes, that is cause of the Huffman codes, and the main things we have generated the entire tree. We have built the tree inside this function build Huffman tree. So we'll be starting the entire codes, and then I'll tell you that how we can write the code. So I'm showing you the output that I got. Look, this is the after compiling the tree I got this Huffman codes, and these are the character that I got. So this was the output. Now we will be understanding the concept. So move back to the concept position. So first in concept portion we will be studying the concept of Huffman coding algorithm. Concept of Huffman coding algorithm, then steps in Huffman coding algorithm, that what are the significant steps that we take to build the Huffman coding algorithm. Next, applications of Huffman coding algorithm. Remember, nobody teaches you the application, but what I strongly believe that we should know applications of all the DSS, all the data structures, that why are you learning those algorithms. So I will tell you the applications, and then the strategy of Huffman coding and its relation to greedy technique, and then I'll teach you that how the Huffman coding is related to the greedy technique. Those who don't know greedy technique, they must follow my first video. I have made you understand the greedy algorithm and its technique in very in depth. So let's start. Huffman coding algorithm. So as you can see, there is characters and there is frequencies. So what we do in the Huffman coding algorithm is, suppose that the dictionary, let's say that wiki code is good place to learn, is good site to learn, so this is a word. Now look, if we count the frequencies of the character, just observe, there is w is for 1 times, there is I, so we got this I 3 times. That means the usage of w in this entire sentence is only for once, the usage of w is only for once, but the usage of I is for 3 times. So what we try to do in Huffman coding, that we try to give the maximum code to the one which has the least number of occurrence. Now look, this w has the least number of occurrence 1, so we will be giving this maximum code. So let's take that all the codes are of 8 bits, so we will be providing it 9 bits, and to this that has a greater occurrence, so we'll be providing it 7 bits. So this is not a lossy, that means we don't lose, we just shift the compression. So here we provide the 7 bits because it has the maximum number of occurrence, and this is Huffman coding, that we try to compress the data structure by providing the greater number of bits to the one which have the least frequency, which have the least occurrence, and we provide the and which have the highest frequencies, we provide it the lowest bit, that means lesser bit that we provide, lesser bits. So let's study it in depth, and this is how the Huffman tree is built. That is the structure that you can see. So we'll be understanding the structure also. So this is Huffman coding. Let's read the theory. Huffman coding is a greedy algorithm used for data compression. So it's a greedy algorithm, number one, and number two, it's used mainly for data compression. It reduces the size of the data by encoding more frequent characters with shorter code. Look, by encoding more frequent characters with shorter codes, that make you understand that here where there is we utilize this w has the least occurrence, and that's why we have provided more bits to it, and this has the more occurrence, and we have allocated less the more lesser bits, and this is how we compress the data in Huffman coding. And less frequent characters with longer codes, and less frequent characters with longer codes. So you got this point. Now steps in Huffman coding. So this was the Huffman coding, how we got it, that this is very easy. Now we will be observing the steps in Huffman coding. So for the Huffman coding, first we calculate all the frequencies of the words. Let's look the words A5. Let's write those A5, B9, C12, D13, E16, and this is A45. So first we count all the frequencies, and this comes under the step frequency calculation. And then second, we build a minimum heap, and for building the minimum, what we use priority queue. We actually use priority queue. So you might be thinking, what is this priority queue is? So priority queue is actually a queue interface that you actually know. But when we insert elements in this priority queue, when we insert, those gets automatically prioritized. Let's say if we insert 5, 9, 45, 13, etc. So it will get automatically prioritized like this: 5, 9, 13, 45, and this is called priority queue. So these are the first elements: A5, B9, C12. So at first step, what we do, that we combine two nodes. At first step, these are all nodes, and at first step we do what? We first pop. We actually use we pop from these are inserted inside this type of queue, and at first step we pop the least minimum two. We pop this one and we pop this one, and then we add those. So it's like this: first we pop, and we pop that, and we store that into some node type of references. So let's call it, this is we pop node left. We pop this element and we store it in here. So it is stored in here. The entire node A5 is stored in here. In node right, we store the second one right, and then we combine those. We add those nodes. After getting, and we make something like this. Now if we add those values, so the next node will be like this: 5 plus 9, 14. So that is the node, and now it gets connected to this. In left side, the minimum will come A5, and in right the B9 will come. So it becomes some structure like this. So if I write entirely in coding languages, so it like this: node. So in node left we use queue.pop. So in node left, if we use, so this is like this: node left, that is equals to QE.poll. So when I apply this function, the first things, this first is polled, and this is automatically assigned here, the first line. Next time when you again use this node.poll, that is equals to QE.poll. The second time we use the same thing. Now our queue contains only those elements, so this time this is popped up, and these all are nodes. So in this way we first fetch two elements. Okay, now coming to more detailed description, then you will be observing. After we got those two elements, what it did, we added those elements into 14. And in terms of programming language, to express the same things in programming language, we create another node, and we call that node internal. So that is node internal, and we create a new node. And in new node we actually express the character portion. Like this, and we add those frequency, that is frequency of left dot frequency plus right dot frequency. So this is the entire thing that occurs here. So let's understand. In first step we have done this. Now in next step, let's remove this. So in first step we have added this one, this one, this one, this one, and now our tree look like this: 14, A5, B9. In second step what we do, now we again insert this 14 element into this queue. That means 14 is again inserted in here. So this is our entire queue. So we again pop the next two elements. So we can pop this next two element. So after these the elements are C12, C12 and D13. And C12 and D13, again we combine those two elements. That means we add those two elements and assign them on a new node. So they are assigned on a node 13 plus 12, this is 25. So they are assigned in a node like 25. Again we insert this node in here, and after that 12 and 13 has been popped. So our next frequency becomes like 16, 45, 14, and this is 25. So at next stage we will again pop the in priority wise. We will in ascending priority wise. So we'll be popping the first map 14 and then 16. We'll be popping those two elements. So it will be like this. The 14 will come in left side and the greater one 16 will come in this side. Now they will be added, and they will be 16 plus 40, this is 13. So we have popped, so it again gets cut 16 and 14, and that is the entire queue. So after this again we insert in the next step. The remaining elements are 45, 25, and we again insert this 30. So these are the remaining elements. So after this 45, 25 and 30, among these three elements we now pop the minimum. Among from this queue we again pop the minimum two elements. So the minimum two is 25 and 30. So it becomes 25 comes in the left portion and 30 comes in the right portion, and we again add them, and the addition becomes 55. So this is again, after this they have been popped out. Again we insert this element into this queue. So it is occurring till we end the route. So now this is 55 and 45. So after this stage in our queue only remains two elements, 45 and 55. So after this stage if we combine this element they become, again we pop those elements. Now this is assigned to left side 45 and this is assigned to right side 55, and again we combine and assign them to elements, and this last elements become the 100. So this is where our calculation is done, and it entirely forms a large tree. So if you want to form the large tree, it becomes something like this: 100. As we see that we have gotten 100 here, this is 100. So first we write it like this: 100. Then after 100 we have assigned in left side we have 45 and in right side there is 55. So there is 55 and 55 is connected with this one, just observe. So 55 and this 55 is connected with this one, 25 and 30. So the another node 25 and 30. And if we just observe, in right side there is 45 of this. Now we'll be observing the previous ones. 30. Now observe, 30 is connected to 14 and 16. So we'll write those two elements, that this is connected to 14 and 16. And 14 is connected to 5 and 9. 14 is connected to 5 and 9. Sorry, 14 is connected to 5 and 9, not 16. 5 and 9. So if you observe from here, I think 1, 2, 3, 4, 5, 6, 7, 8, 9. All the elements we have used. So this is A5. This element is A5. This is A5. This is B9. Now after this is C12. We have missed C12 somewhere. 25. This is, here is C12 and 13. C12 and D13. So this is C12 and that is D13. So that is the entire tree that we have got. That is the entire tree and these are every node. Now what we do in the Huffman tree, that we find the binary code of all those values. We try to find the binary code. So how do we find it? Let's write it. So if we study code, we have built the Huffman tree. Once we have built the Huffman tree, after building the Huffman tree, after building the Huffman tree, we find the binary code. We try to find the binary code. So we write code for everyone. So the letters are A, B, C, D, E, F. Now observe, whenever we traverse from here to there, if we traverse on the left side, then we assign 0, and if we traverse in the right side, then we assign 1, right side, then we assign 1. So now we try to find for A. So what is it? This is A. So we are traversing from here. This is right side, so we will be substituting 1. When we traverse from, look, when we traverse from here to right side 55, we put here 1 because this is the right side. Again, when we traverse from here, because we want to come to A, this is our goal where we want to come. So again, when we come here, again we put 1. Why? Because this is the right side. If we traverse in the right side, at the node position we'll put 1, and if we traverse in the left side, we'll put 0. So after that, now that is A. We need to traverse from here in the left side, and because this is left, we'll be putting 0. Now again we have to traverse in the left side, so we'll be putting 0. So that will be the code for our A. Now we'll be finding the code for B. What is the B? This is B. So we have already traversed this, these are same. From we are traversing from here to there, this is the right side, so the first 2 digits code will be same, 1 1. Now look, again we are traversing in the left side, that is also same 0, and now we are traversing in the right side, so we will be putting 1, so that is 1. Now we will be finding for C. Now we'll be trying to find for C. What is C? This is C here. Now look, this is from where we start, and we are traversing in the right side, so we'll be putting 1. Then after this right side, that is our C, so we are traversing from here in the left side, so we put 0. After that we are again traversing in the left side, so we again put 0. We are putting for left, we are putting 0, and for right we are putting 1. Now we will be finding D. So if you observe the D, the entire track from here to here was similar to C, except the last, that it has traversed in the right side, and so we'll be putting 1. So similarly we will be putting 1 0 1. This is for D. Now if you observe for E, what is the E? E16. This is E16. So we'll be coming here, so the traversal is towards the right. This is right, so we'll be putting 1. This is right, we'll be putting 1. This is right, we'll be putting 1. So 3 times we got right, so 3 times we'll be putting 1 1 1. And F, now we need to find F. F is 45, and this is 45, and this is in the left section, so we'll be putting 0 for here. So in the F we'll be putting 0. So this is the construction of Huffman's coding algorithm, that we figured out the codes, we figured out the binary code values, what values to assign, and now we need to build this entire binary code from through the algorithm. So if you observe this, let's study the theory, that is steps in Huffman coding. Build the Huffman tree. This is the track how we can build. First remove the, so I made you understood, will be frequency calculation. First, in first step what we will do, we will be calculating the frequency, building a minimum heap. In second step we will be building up minimum heap, we will be building a priority queue where we will be storing all the elements. We have stored all the elements, those all elements we will be storing. So this is building a minimum, that is second step. Third, removing the two least frequency nodes from the heap. We have removed always the two least frequency nodes, from the heap. Create a new internal node. Then we have created a new internal node. So in program also we need to create a new internal node. Then after creating those internal node as the children with a frequency, insert the new node. Then we will be inserting the new node back into the heap. That means after that you can observe that we have inserted back into the heap. Repeat until only one node remains. So we'll be repeating until only one node remains, and look, observe. At the end we continue till we got 100. When we got the 100, the highest value, this is when only one node was remained. Then we stopped. Generate code. Traverse the tree from the root to labels, assign 0 to the left edges. Now look, assign 0 to the left edges. Whenever we'll be traversing towards the left, we'll be assigning 0. And whenever we'll be traversing towards the right, we'll be assigning 1. So we have done the same, that we have assigned left 0 and right 1. And this is the construction table of binary codes that we have constructed. Now look, now we'll be moving toward the coding section, and here we will actually not see the code and we will not understand the code. We will understand the theory, and from theory we build the codes. So let's make this. We'll be making this tree in the next. Here. So first what we got, 100. That is 100. Let's make it here 100. And with the node of 100, after this node, what we got from our tree, we got 45 and 55. So we'll be noting down that 45 and 55. After 45 and 55, we are getting 25 and 30. So we'll be keeping those 25 and 30, 25 and 30. And after this 30, this is coming from 14 and 16. 14 and 16. And at the end, this 14 is coming from 5 and 9. 14 is coming from 5 and 9. Now this 25 is coming from 12 and 13. 12 and 13. 12 and 13. So this is the entire tree, and now we'll be writing the program from this section. We'll be writing the program, that how we can write the program. Now look, observe these nodes. These things, these are a nodes, these are a nodes, these are a nodes. These all sections are a nodes. We call them nodes. And what type of node? It has no definition. We have to provide the perfect definition of this node. So first, for providing the perfect definition in Java, we have to create a node class. So we will be creating a node class. So if you observe this node, if you just zoom or scan this node, what is this internal structure? So you will be looking like this. All the nodes. This is not just for this node, this is for this node, this node, this node. All nodes structure is same. These nodes look like this. There is a character. There is a variable character where there is stored. Let's say that this is here, this is the root is stored, character root. And now there is a frequency. There is a frequency. So here the frequency is stored, and the total frequency is 100. So here 100 is stored. Now look, every time there is a left. This is left side and this is the right side. So these are called the pointers. This is called the left pointer, and this is called the right pointer. That is called the left pointer, and that is called the right pointer. So there is more place for left pointer and right pointer. This is for left pointer, left, and that is for right pointers. Pointers. And now we need to write this. We need to construct this in our Java code. So let's look how we can construct this. So first we'll be writing this class. Whenever we create any node data type, we need to build a class. So we'll be building class in Java like this. Class node. Once we have written class node, we will be initializing all the variables. We will be initializing this variable. So this is character. Let's call it character, because we'll be storing characters A, B, C, D. We'll be storing all those characters. So this is character. Second, this is done. Now we will be inserting frequency. So this value is an integer, so we'll be writing integer frequency. Now there is pointer, left pointer, right pointer, so we'll be writing node left, right. So now we have declared, this is called the declaration of variable. We have initialized or declared the variable. So after the declaration we'll be constructing node class. So let's call it node, and let's call this character. This is parametric constructor, and it is the frequency. When we are creating, so we pass this value here. Look, this is a5, so that was a5, we passed the value as a5, so a each passed, 5 each passed, and those values that are not passed, that is passed as 0 0, that is null. So entire this value is passed, so we'll be writing character frequency, integer frequency, and now we'll be assigning them to this dot character, this dot character equals to character, this dot frequency equals to frequency. So that is frequency, and now we'll be assigning null. Look, character and frequency was passed, so we assign them in quotes, but left and right is not passed, so we'll be assigning them with the value of null. Left equals to right equals to null, so they are assigned with null. So that is the basic construction of node. First we create the node. After we create the node, second step we create the comparator class. That means we create a heap, we create the queue, priority queue, and for that we create our custom comparator. So in second step, creation of custom comparator for priority queue. So now we create a custom comparator for priority queue. And for that also we need to declare a comparator. We create a new comparator class. So now we'll be creating a comparator class, and that is class node comparator. So we'll be writing like this: class node comparator implements, because it will be implementing already a pre-existing comparator class. So implements class node comparator implements comparator node. This is, and now we'll be starting our class, and now we'll be declaring a method. So let's name the method as compare, public integer compare node A, node B, return A dot frequency minus B dot frequency. And now this section, that the custom comparator we have created here, this automatically provides three values. It will provide either value -1, or it will provide 0, or it will provide greater than 1. Look, if this is greater, then we'll be get positive value. If this is less, this is negative value of 0. And depending on these three values, it will automatically sort the entire queue. So because of this custom comparator, whatever the values will be in this queue, that will become a exact true meaning priority queue. That means automatically the value will get prioritized. If there are 3 9 4 1 2, so it will automatically get prioritized like this: 1 2 4 1 2 3 4 9, like this. So we have created. Now we will be constructing that how we can build the tree. We'll be observing that in here, and then we will also write the entire code. So in the next topic, next page. Here we'll be observing that how we can write the method. So we'll be writing the entire method inside the main class. So first we'll be writing our file name like this: public static void main string out, as we do in Java. And then look, there is a character array, so we genuinely create that character array. What's already written. So we create a character character array. So we are creating this character array like same. We'll be inserting like same A, B, C, D, E, F. This one. Now we create the integer frequency array. So same, we just write it here. Integer, we write like this: character frequency, and this is 5, 9, 12, 13, 16, 45. Now we'll be creating our priority queue to stage all the nodes using the custom comparator that we have created in here. So we'll be now building a custom queue using this custom comparator. So let's write code for that one. Priority queue. Priority queue node queue, new priority queue, new node comparator. So we have created a queue with respect to utilizing the custom node comparator. After that creation of all things, now what we need to do, that we need to add all the elements, all the nodes available, we need to add into this queue. Now our main work is to add all the nodes. These are everything's value of nodes. So we will be adding those nodes of all those data types into this queue. This is, and for that we will be using just a for loop. One for loop is enough to traverse the entire nodes. So for integer I equals to 0, for integer I equals to 0, I less than character array dot length. So it will run up to this entire length I plus plus. And now we'll be adding this QE dot add, and now we'll be invoking that constructor of node class. So new node, and we'll be passing character array in the place. So all those values character will be passed, character array of I comma, and now we'll be passing the character frequency of I. So now all those values will get automatically added to the queue. After we have added all those values, after we have added, what it did in the next step, that after adding all those values, we are picking two items. So we'll be picking two items from the priority queue. We are picking this item and this item. So we'll be picking that item, and then we are adding those items. After picking 5 and 9, we are adding those, and it would return as 5 and 9, that is 14. And we are getting this 14, and we are again inserting back into that. So we'll be writing codes for that 9. Now we'll be picking the 5 and 9. So for that we'll be using, and we'll be picking when there is the base criteria, till the length will be greater than 1, when at the end it becomes 100, that means one element we don't pick anymore. We pick only when the length is greater than 1, that is 2, 3, 4. So we'll be writing code for that. Okay, now we'll be picking those elements from here till that is greater than 1. So for that we'll be picking those elements, and only when the length is greater than 1. So we'll be writing the code like this: while kiwi kiwi dot size that is greater than 1. That means there is all at least two elements. At least two elements. Then only will be running this code. Node left equals to, will be picking the first node. These are stored like nodes in format of nodes. So node left equals to kiwi dot poll. So it will retrieve the element and remove from the list. Node right equals to, again, now it has been popped. Now again kiwi dot poll. So now in right also we popped out the elements. After we got the elements, now we'll be adding those two nodes, because after we got 5 and 9 in Huffman algorithm, we had to add the two nodes and we have to write that code. And what we need to do, we would store those into a extra node. The 5 and 9 we need to add and store it as a form of node. So we'll be creating a node, and let's say this node is internal. So we'll be creating another node internal. So we'll be creating another node internal. In the same way, new node. We constructed this node, and now there is no character. This is the addition. So in position of character, we pass just a dash here. And now we'll be adding. What we are adding? We are adding the frequencies. So from node, this left node will be access the frequency position. So left dot frequency, left. So we'll be adding the frequency, that is left dot frequency plus right dot frequency. So now those will be get added, and now the node will get constructed like this. Now our node 14 will have actually constructed. Now look, we need to point this also, this 5 and this 9, these are connected through pointers. So we need to again connect those also with that node, and for that we need to create the entire node. So now the node is like this. There is 14, it has been created, and there is this dash has been also created. So now if you look this node, it looks like this. The node is, there is a dash. As we inserted the character, it comes here, and now they have been added. So 14 comes here, but this is null. That means they are not pointing to anyone, and we need to point to 5 and 9. As this is, we need to point. So for that we will be again in node portion will be assigning that value. That means internal dot left equals to left, internal dot right equals to right, and now kiwi dot add of internal. So now we add the node, and once we added the node, now the addition of 5, those 5 and 9, that is 14, will get added to this kiwi. That will get added from there. So this is the code we wrote. Now after all the portions have been done, we need to point the root node. So for that we'll be writing node.root equals to kiwi.poll. Once we have done this kiwi.poll, it will provide the root node 100 in this position, the root node, and then we'll be print the Huffman code. The code for printing Huffman, print Huffman codes root, and we're again passing null. So this was the code how we can compose the etc thing. So suppose if we want to print this print Huffman code. So for that we need to write the function also. So let's see how we can write the function of print Huffman codes. So if you observe the tree, now look, this is the root node, that is the root section of the node. So we state from the root, if this root position is null, that means there are no elements. This is null, this is void, that means this is 0, there is no those connections, that means there is nothing we will be returning from there. And if the root position is not, look, here are lots of elements are connected with this. So these are the places when we have no character. That are the places when we have no character. And if that is not present, that is look those position. This is not of this. That means here this character is lacking. That means there is a absolute character. So we'll be entering into that. So first we'll be checking this criteria, then we'll be checking this criteria, and then this. Just observe it. All the things patterns are same. This pattern is same, this pattern is same, and this is both in the left side and in the right side. So for that we'll be use the recursion. We'll be using recursion, and whenever we'll be using recursion, we'll be provide the one base case. So let's write the code for there. Public class Huffman coding. Public class Huffman coding. Public study void print Huffman codes. Print Huffman codes. And now node root, as we passed root from there, from wherever we called, and string code, so we passed just there. So now we'll be checking the first condition. Here we have initialized, and we'll be checking the first condition, that if root is null or not. So first we'll be checking if root equals to null. If root equals to null, so we'll simply return. Okay, now we will check if root is not null. The second criteria I saw you. If root dot character not equals to this, so we'll be printing system dot out. That means there is absolute a character. Root dot character. Root dot character. Root dot character. So this is, now we have printed the main things, and this we have to print for all the nodes. For that we'll simply use the recursion, but in a way that the elements will start ending. So for that we'll apply recursion. Print Huffman codes. Print Huffman codes root dot left comma code plus 0. Print Huffman code root dot right, and now the function is being closed. So that was the code for the Huffman coding. Before we end the lecture, it becomes so large because of so much concept. So we'll be observing where we use the Huffman coding algorithms. So first, if you observe file compression, we utilize this in file compression, that is mainly used in zip or zip or zip formats for lossless data compression. It's also utilized in multimedia compression. Huffman coding is also utilized in multimedia, applied in JPG image compression to reduce file size, used in MP3 audio compression for efficient audio file storage. Now data transmission, optimizes data transmission. It's also used in data transmission. Text comparison, this is also used in text comparison, compresses larger text files, example Unix compression. So in these are all the places where the Huffman coding algorithm is utilized. Now data structure, constructs optimal prefix free coding schemes, optimized for efficient data representation, compresses log files and data in operating system. It's also utilized in operating system. Telecommunication, used in early fax transmission to minimize documents in documentation. So while we are transferring the fax, we are utilizing this Huffman coding algorithm. Optimizes memory usage in compiler, also these are also used. So there are a various lot of utilization of Huffman coding algorithm. Actually I made you the coding, and coding is a bit anonymous topic, so the video become very large. So I don't know if you like this video or not. If you want in more detail or in more modulated format, tell me, so I will making the video. So we'll be meeting in the next session. I don't know, that is I think dynamic programming. So okay, thank you, that's well.